Many people find it useful to look at the periodic table as if it were a calendar. So as you'll notice a calendar, you've got dates going across. You've also got days of the week going down. And this is where we get into some similarities between a calendar and the periodic table. Monday means certain things to you probably. Generally, every Monday for most people, that's the day you go back to work or the day you go back to school. Personally, I always get really excited about going back to work, but some people say I'm weird in that way. Likewise, you may have something that you always do on Tuesday or Wednesday. Maybe you've got a teacher who always gives you a quiz every Wednesday, or maybe there's a TV show you watch every Tuesday night, for example. And finally, we get towards the weekend or the end of the week. The weekends are often greeted with a great deal of happiness, or at least some relief. So in this sense, you start to see how what's going on in each column is the same. Now, Monday the 3rd is completely different from Monday the 10th. They're completely different days, different things happen there, but all Mondays have some things in common. Likewise, all Fridays will have some things in common. All Saturdays have certain things in common, and so on. In the same way, you can imagine a periodic table. Elements that line up in a column have certain properties in common with each other, and that's why they line up in these columns. You can imagine a week that starts on the 2nd on a Sunday, and it goes on and on up until the 8th, which is the Saturday, and then this whole period of time starts over again. We started a new period, and once again we're on Sunday. So Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, another period, and now we go back to Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and so on again. So just as these rows follow a certain period of time, or a period, which then starts over again, and we go back to the beginning of the same characteristics or the same kind of day, elements follow the same thing. So you've got several elements in this column that have similar traits. This column, they have similar traits, and so on. So you get to here, and then we move back. We finish this period or this row, and now we go back to the next row and start a new period. This is one of the reasons it's called the periodic table of the elements. So think of the periodic table as a calendar, and this might help you make more sense out of it. So we're looking at a very simplified periodic table of the elements. I got this picture off of Wikipedia. But you'll notice that the numbers across, which refer to these columns, the columns going up and down, are called groups, so that we've got group 1, group 2, and I'll circle that just so you can see that a group is basically vertical. It's a column. Group 2, group 3, 4, 5, and so on. There are 18 groups, and if you want to use the calendar analogy, each group roughly corresponds to a day of the week. That means the elements in the group are not exactly the same, but they have many similar qualities. The same way that not every Saturday is the same for you, but every Saturday has some traits in common. Now if we go across, we have what are called periods. So again, we have period 1, 2, 3, and so on, and I will circle this just to show you that a period is a horizontal section of the periodic table. And once again, there's a pattern as you move from left to right in a period, and when you get to the end of the period, you then jump back to the next period. And again, the pattern from left to right continues, just like an individual week on a calendar. And we're going to look at 3 traits that can be predicted by the periodic table. One of them is the atomic radius, that's telling us how wide an atom is based on what we know about it from its position in the periodic table of the elements. The other trait is the ionization energy. This is the energy it takes. Essentially, you could consider the energy it takes to cause one element to react with another and form a chemical bond or break a chemical bond that already exists. So it's the energy needed to cause a chemical reaction to happen. And the third item is electronegativity. Remember, that's the ability of a given atom to take electrons away from another atom. So to make sense out of these 3 characteristics, let's look at what some of these elements mean. Now let's take lithium as an example. Lithium is in the 2nd row. It's period 2, group 1. And lithium has an atomic number of 3. This means that lithium has 3 protons in its nucleus. Now the atomic mass will be different in many elements than its atomic number, because the atomic mass also includes neutrons. But for the characteristics of an element, the number of protons in the nucleus are paramount. Now lithium, because it has protons, you would expect a lithium atom to have an inherently positive charge of, we'll say, 3. And therefore, under normal circumstances, it would attract 3 electrons. As we go across the period, we'll notice that the number of protons increases by 1, so that we've got 4, got 5, 6, and so on. And let's think about how this might affect the electronegativity, the atomic radius, and the ionization energy or reactivity of these elements. When we go from 3 protons to 4, we're going to, of course, normally add another electron as well. But now we've got 4 protons, which are going to have a strong attractive force. This means that the electrons will be slightly closer to the nucleus because they're attracted more strongly, and therefore the atomic radius decreases. So the radius is, we'll just graphically show this. Let's say we've got an atomic radius here. This atomic radius will be slightly smaller. We look at carbon, we've got 6 protons, and therefore there's going to be a stronger attractive force. Those electrons are going to be pulled in closer towards the center of the carbon atom, so the radius of the atom will be even smaller, and continue on with nitrogen, oxygen, and so on. We get to neon, this will have the smallest atomic radius. But now we're going to jump back, and suddenly when we get to sodium, there's a somewhat larger atomic radius. So in the periods, as we work our way across a period, the atomic radius, or the entire diameter of the atom, decreases. It actually goes down because the electrons are more strongly attracted. Likewise, as we go across a period, the ionization energy will increase. That is, it will take more energy to cause an atom to react. As you have a larger nucleus with more protons in it, there's a stronger force holding in the electrons, so they're less likely to move and become shared with another atom. In fact, when we get to the very end, we've got the noble gases in this final group. And the noble gases are called noble because it takes an incredible amount of energy to cause them to react with any other elements. So these noble gases have the highest ionization energy. That is, it takes them the most energy to react with other atoms. And on the other hand, Group 1 is very, very reactive. That means it takes very little energy to cause these elements to react with something else. So what do we know about atomic radius? If we're going down in a group, the atomic radius will actually increase. Let me explain why. In this case, we're making a jump from 22 protons to 40 protons. This is going to correspond with a huge increase in the number of electrons. This means more of the orbitals or energy levels will be filled, and so there will be electrons moving further and further away from the nucleus. This more than counteracts the attractive force of the extra protons. And so as you go down in a group from top to bottom, you greatly increase the atomic radius, the width of the atom. As you go across a period from left to right, the atomic radius decreases. As you go down a group from top to bottom, the atomic radius will increase. Ionization energy has a similar correspondence. As you go across a period, the ionization energy will increase. That means it takes more energy to react because the electrons are being pulled more closely towards the nucleus of the element. As you go down a group from top to bottom, the ionization energy decreases. That is, it takes less energy to cause one of these elements to react as you work your way down. Because the electrons are flying in orbitals further and further out away from the nucleus, they're less inclined to stay with that particular atom and more likely to move to another atom, therefore causing a chemical reaction to take place. At this point, you may have realized the importance of the outermost energy shell of electrons in determining how an element is going to react with other elements. If you take that into account and you remember that the periodic table is arranged by the number of electrons and their positions, you can see now why we divide the periodic table into these different blocks, and they're shown in some colors here. These blocks are based primarily on the outermost electron shell. For example, the first two groups form what is known as the S block. I'll put an S right there. The S block, because their outermost layer is an S orbital. Helium, by the way, also has an S orbital, so I'll just circle that and put an S over helium. However, groups 3 through 12, their outermost shell is going to be in the D block, so we'll write D block, because their outermost electron shell is the D orbital. And over here we've got the P's. So groups 13 through 18, with the exception of helium and a few other exceptions I'll get to in a moment, they have p orbitals in their outermost shell, so they're called the p block. Now we've got the F block down here. Elements 57 through 71 are actually in group 3, but they have an F orbital on the outside, so they're part of the F block. The same for elements 89 through 103, even though they are also in group 3. So there's this one exception in group 3, which is known as the F block. We'll be looking more closely at these blocks in another video. So thanks for watching.